One common thing we want to do with derivatives is to be able to talk about them in a meaningful way, as opposed to just thinking about it as a slope. So sometimes it's going to be contextual and understanding its units and what it represents in the particular real world scenario is really beneficial in many applications. So to understand the units of dy dx, remember that this expresses a change in y divided by a change in x. And the reason we use dy and dx instead of what we have seen in an algebra class, delta y and delta x, is this is an average rate of change, but derivative is instantaneous. And all that means is that if we were to create a microscopic change in x, that would tell us by how much the value of y should change by per unit of x. So it gives us a ratio of something to 1, but it doesn't mean that we're actually, that value says if you change x by a whole 1 unit, then y will change by whatever amount, right? We're saying that this is a ratio corresponding to just miniature changes in x. So if I have a curve that looks like this, and I calculate the derivative here, and I figure out the slope, well, if you notice that slope looks like it's locally linear to that point, but as I get farther and farther away, maybe even as much as 1 unit, I go from some x value to x naught plus 1, well, you can see that we've deviated really far from where this curve actually goes. And so even though it's a ratio of per 1 unit in x, we usually don't use it to change the value of x by 1, although we could for an approximation. So here is a sample function, so we can get our senses about this. The function a of r equals pi r squared. It gives the area of a circle. A in square inches as a function of the radius of the circle r, which is in inches. So first of all, we can think about what the function outputs, and given a value of r, in this case, the radius is 10 inches. So a circle, we could start by saying a circle with a 10-inch radius will have an area of, well, we need to calculate that. So a of 10 would mean that we have to calculate pi times 10 squared. And that comes out to, we'll just round to the nearest tenth of an inch. So 314.2 inches, square inches. And so that would be the area of our circle, 314.2 square inches. So notice that the units of both the input and the output they're not rates, they're just static amounts. 10 inches, 314.2 inches squared. Now, let's calculate a prime of 10, so that requires taking a derivative. And also, by the way, a prime is the same thing as saying dA dr. Right? That's the derivative of a with respect to the variable r. And so the function itself would be 2 pi r. That would be the derivative of pi r squared. And now we want to evaluate this thing. By the way, we could just write a prime of 10, or we could also say dA dr for r equals 10. That's just another way of saying evaluate that function at r equals 10. So we'll have 2 times pi times 10, which should give us, let's see, around, 62.8. So this comes out to 62.8. But 62.8 what? Well, keep in mind that this is a rate of change, right? And so right now it only shows the change in one quantity, but we could always put it over 1. Right? You can always take a number and put it over 1, and that expressly now gives you a comparison of one quantity to another. And this means that if you change the radius by 1 inch, if you increase it, then you would expect a 62.8 square inch increase in the radius. Okay, so, but this specifically pertains to a 10-inch radius circle. So here's what we should be thinking. If I take a circle, and there's my circle, right? And we'll just say that this has a radius of 10. If I were in theory to increase this circle to have a radius of 11, well, close enough, then that would mean that I would expect that area to increase by 62.8 more square inches. So in other words, this right here, corresponding to a radius increase, and I'll just mark the radius here as r equals 11, that I would expect that purple area that I've just shaded in, right, that purple area would be 62.8 square inches of additional area for a 1 inch increase in radius from 10 to 11, right? Because if we went from 11 to 12, well, then we'd have to plug in 11 for the radius and we'd get a bigger value. So for a 1 inch change in radius, the area of a circle, the increase of the area gets larger and larger as that 1 inch increase is on a larger and larger radius. So I will state it like this. For a circle with radius 10 inches, if you increase the radius by 1 inch, we expect, or we estimate, a 62.8 square inch increase in area. So basically, we would be at around, if you took 314.2 square inches, which is the radius or the area of this circle here, that would be the 314.2, and you added the increase to it, that would give you, let's see, 377 approximately square inches. But keep in mind, this is not correct, right? That's not the actual increase, because that's based on the idea that we change the input by a whole 1 unit. And we know that, where we end up and where we should end up could be 2 different values, because that rate of change is just locally valid. Okay? But we can still do some approximations with it. So here, to get a of 11, what I could do is take a of 10 and add a prime of 10 to it. So in other words, that 314.2 plus the 62.8, and as we said, that should give us the 377 square inches would be our approximation, okay? So we're saying estimate, that's the key here. If you actually plugged in 11 and you did pi times 11 squared, the actual area is 380.13. So I'll just say actual would be 380.1, and you can see that this is based on the function, and we're not too far, but you can see that we are off, right? It's not exact. Now to get a of 10.1, well, let's see, if I took a of 10, I don't want to just add a prime of 10, right? Because this represents the number of square inches, and this represents that 62.8 square inches, but that's for a 1 unit increase in the radius. But I'm not increasing the radius by 1, I'm increasing the radius by only 1/10 of that. And therefore, I would have to increase the area by only 1/10 of that approximation. So the idea back to our picture here is, if I don't go the full 1 unit, but I only do 1/10 of that, then proportionally I should only go up 1/10 of that full rate of change in y. And so now I would get the 314.2, and 314.2 plus 1/10 of that would be 6.28. That would give me an approximation of 320.5 square inches, right? And what we should notice, if we actually compare that to the actual, where I would, plug in 10.1, so I would do 10 or pi r squared, pi times 10.1 squared, I get an actual of, look at this, 320.5 square inches. Now there is some rounding error. There is going to be some rounding error there because I just rounded off to the nearest tenth. So, but look at how much closer it is. So increasing your time by just a little bit keeps the output values more consistent with the exact area function than if you were to increase the input by 1. And this just goes along with that idea of local linearity. So why would we even do this? I mean, why are we even adding the derivative or some multiple of the derivative to the output value? The reason we're doing this is because a lot of times we're not going to be dealing with algebraic functions. We're going to be dealing with numerical functions, especially in the context of machine learning, where computers are using very good approximations and sort of fine tuning those, and they can do a lot of iterations. So we can actually do things like hunt for minimums and maxima by using the derivative and just increasing or changing our output value by very little increments of that.